My name is Yechoshu. I am excited to introduce our work PredLDM, Spatiotemporal Sequence Prediction with Latent Diffusion Models. Let's start with the problem. Spatiotemporal sequence prediction is about taking past frames and predicting what comes next. This direction serves diverse real-world applications like weather forecasting, self-driving cars, robotics or human behaviors. In this paper, the challenge lies in given these historical observations, can we generate accurate and realistic future frames? Existing approaches have some fundamental limitations. Deterministic models, like Convel-STM, tend to minimize mean-squared error, which often results in blurry predictions. Probabilistic models like GANs or VAEs, they generate sharp images but they're prone to mode collapse. Recently, we've seen amazing results from latent diffusion models in text-to-image and text-to-video generation. Models like Stable Diffusion and Sora show incredible visual quality. So we thought if we could adapt these powerful models for our prediction task by introducing LDMs. But it's not just a simple transfer. There are two main issues we need to address. First, how do we model complex temporal dependencies across the entire sequence? Traditional 3D convolutions and 2D plus temporal layers have limited receptive fields. Second, in text-to-video models, the condition is text, which is high-level and semantic. In our settings, the condition is historical frames, with much more complex and low-level signals. So we propose PredLDM. Our framework has two main stages. First, we compress the video into a meaningful latent space using what we call MTVAE. Then, in the second stage, we use CALDM, our condition-aware latent diffusion model, to actually generate the future frames. For training in the first stage, we use transformers with masked self-attention to construct MTVAE, forcing the model to learn more robust temporal and global representations. Unlike typical diffusion models that just generate from conditions, we do two things simultaneously in the second stage. We learn to generate future frames given history, but we also learn to reconstruct the history itself. This dual learning helps the model really understand the conditional information better. For inferencing, noise sampled from Gaussian noise is fed into denoising network fused by encoded conditions iteratively generating future latent vectors. The decoder finally produces future outcomes. We evaluate on three very different datasets. Kitty-Caltech for driving scenes, KTH for human actions, and Sevier for weather prediction. From main results, our model achieves the best scores on most metrics. Particularly in LPIPs, 30% improvement on Kitty-Caltech and 12% on KTH. Temporal analysis on FVD and KVD scores, which measure distribution similarity between generated and real video sequences. PredLDM achieves the best results here, indicating that not just individual frames, but the entire sequence looks more natural. We have done extensive ablation studies to understand what's driving our performance. Comparing different autoencoder designs, our MTVAE clearly outperforms both 3D VAEs and 2D VAEs with temporal convolutions. Removing our condition-aware reconstruction loss hurts performance significantly. This shows that helping the model understand the conditions themselves is crucial for good predictions. We also experimented with different masking ratios in our attention mechanism. A ratio around 0.6 works best across all datasets. This regularization through masking helps the model learn robust representations. Evident reduction in cumulative error can also be observed, revealing promising future for PredLDM applied in real-world applications and future research. Thank you.